Hello everybody, welcome to Blue Marble Science. I was going through Jeranism's channel the other day looking at some recent videos, and Jeranism thinks he can prove science has been lying to us. Well, you know what? I'll bet we can prove somebody's lying. Jeran Campanella thinks he's come up with some concrete proof that we've all been lied to. Now, unfortunately for him, my Samsung smartphone has got something else to say about that. So Gladys, you think you can pick out the other jackass in this video? Yeah, I'll bet you can. Let's light this dumpster fire and have a little fun. So Jeran's going to try and prove that the science books, all of physics, and the totality of the engineering community have just been lying about the centripetal force. And he can prove it because, well, reasons. This particular train wreck starts off with a general dismissal of math by Jeran over something called Aleph Null. It's that funny looking thing. What you're going to hear first is Jeran pull a couple of sentences out of the middle of a 24-minute video by Vsauce. The title of the video is How to Count Beyond Infinity. It's kind of a theoretical mathematical thing that, quite frankly, I don't understand, but it doesn't have any application in the world of physics to begin with. Nonetheless, that doesn't prevent Jeran from cherry picking. Almost makes me wonder if he's related to Quantum Eraser or something. Anyway, I'll put a link to that video, by the way, in the comments section. It is very interesting to watch. But for now, let's listen to Jeran do his thing.
Now, we're about to talk a little bit about math, and so I hope people understand that despite what you might hear elsewhere, math is not reality. Math is a human creation, and while it may describe reality, it cannot prove it. Why? Well, because we invented it. If the foundations are wrong or the axioms are off, then it can appear to be reality, but it is nowhere close. Math is math, not science. Math is the culprit here. Things that are said to be true because we say so. Because Einstein wrote some equations that say that space-time can be bent, doesn't make it true that space-time even exists, let alone that it can be bent. It's math. The human conception that ignores experiment but instead builds its knowledge around agreed-upon equations. In a Vsauce video titled How to Count Past Infinity, Vsauce states, and I quote, "This is math, not science. The things we assume to be true in math are called axioms, and an axiom we come up with isn't more likely to be true if it better explains or predicts what we observe. Instead, it's true because we say it is." End quote. Ah, it's true because we say it is. Well, good thing we can never fall victim to being fooled through math. Oh wait, it's actually a perfect way to be fooled. He goes on to say, and I quote, "Its consequences just become what we observe. We are not fitting our theories to some physical universe whose behavior and underlying laws would be the same whether we were here or not. We are creating this universe ourselves." End quote.
Well, thanks for that, Jeran. Math has a definition, and no place in the definition does it talk about just making up things. It includes algebra, calculus, trigonometry, a bunch of higher level math that has allowed us to do some pretty wonderful things. We wouldn't have the machines we have today. You wouldn't be communicating the way we communicate using the computers we use or living in the houses and buildings that we occupy on a daily basis if it were not for math. Now, the fact that you're not very good at it doesn't diminish the fact that math is extremely important. So Jeran goes on in an attempt to convince everyone that physicists, scientists, they're all lying to us. And he's going to prove that to you by showing you how little he knows about the world he lives in. Watch this.
Okay, so are we spinning? First, whenever we're discussing this topic, many people will want to use angular speed. Why? Well, because the angular speed is the same no matter where you might be on Earth, while linear speed is simply distance over time. So we can make this simple with this simple circle animation. Consider first this circle is a merry-go-round with a circumference of 100 feet. Now clearly, to anyone who can just think at all, the blue dot, and we can pretend these are horses since this is a merry-go-round, the blue horse moves faster over a given time. The green horse moves the slowest because of the equation distance over time. The blue horse is going around 100 feet in, say, 4 seconds, but the green horse, which has a much smaller circumference, is going only 10 feet in that same 4 seconds. But if we use angular speed, well then both the green horse and the blue horse have the same angular speed, but very different linear speeds. The blue horse is going 25 feet per second, and the green horse is going 2.5 feet per second, 10 times less. This makes sense. Someone at the center of the merry-go-round will definitely feel a different speed than someone at the edge. However, if we use angular speed, as most globe proponents will want to do, then the speed of the horses is all the same. They're all moving the same angular speed. The blue horse on the outer edge and the green horse towards the middle. So it makes sense why they want to use radians and talk about angular velocity, because they would be the same. But we know someone at the outer edge of the merry-go-round would always move faster than someone near the middle. Here we have an article from fizzlink.com that asks, if I'm on a merry-go-round with a friend and the friend is closer to the center than I am, are they going faster than I am? And the answer is no. You're going faster. The merry-go-round is rotating with uniform circular motion. That means that it rotates at a constant angular speed. They then go through a little bit of the math, which again shows that if you mean linear speed, then someone at the outer edge moves fastest. But since you're both circling with uniform circular motion, you are both moving the same angular speed. But again, the closer you are to the middle, the slower your linear speed is. The next little trick that globe believers use is to say, well, yes, we are spinning 1,000 miles per hour at the equator, but we're only going around once per day. No one could ever feel that. Well, in a sense, they're most certainly correct. On our merry-go-round here, if the blue dot moved around at, say, 1 rotation per day, you wouldn't even know it was moving. It would be so slow. But here's the trick. Remember, this merry-go-round is only 100 feet in circumference. So let's extend that to, say, a mile. So now the merry-go-round goes around 1 mile per day. Now, would the blue horse know that it was moving? Well, just barely. Not quite like grass growing, but if you looked out, you would be able to tell that you were moving. But it would be very, very slow. You'd be moving at about 1/25th of a mile per hour. But to see if we'd notice flying 1,000 miles per hour at the equator, we'd have to take that small speed we were just talking about, that 1 mile per day, and multiply it by 25,000. Think of anything moving at any noticeable speed, and then think times 25,000. It's ridiculous. Think of seeing a car drive by at 30 miles per hour. Okay, well, 25,000 times that is 750,000 miles per hour. Ridiculous. So think of a car going 1 mile per hour. Now times 25,000, that's 25,000 miles per hour. So I hope you can see how insane it is to multiply any speed by 25,000. But that's what we need to do to compare it to the speed that we're moving on the Earth. That merry-go-round at 1 rotation per day, which is 1 mile per day, needs to be multiplied by 25,000.
Whoa. Wait a minute. What did that knucklehead just do? He assumed the circumference of the Earth is 25,000 miles. Okay, I'm all right with that. But then he took the speed of a car at 30 miles an hour and multiplied that by 25,000 miles and came up with 750,000 miles per hour. What? That's miles per hour times miles. That's square miles per hour. What the hell is that? The speed of real estate? Then he backed it down to 1 mile per hour and got 25,000 miles per hour somehow or the other. I guess that must be for one of those smaller lots in the back of the trailer park, huh? Jeran, stop, man. Just stop. You're giving me a migraine. I think we found the other jackass. Gladys, what do you think? Hey, I'm not going to say that. You'll have to tell him that.
The speed would send anyone flying off the Earth without a doubt. Let's get back to our example and how it compares to Earth. But my hope is that you realize why I think angular velocity is just not needed here and why globe believers will jump to use it. They want to use angular speed because they want to say that both the blue dot or the gray dot, the red dot, and even the green dot are all going the same speed. Angular speed lets them do that. Linear speed does not. So linear speed says that the horse on the outside has the greatest linear speed because obviously it has a greater radius. And angular speed says the speed of all the horses is the same because they all make 1 revolution in the same time. Okay, moving on to a globe Earth, since we know linear speed is simply distance over time, we can easily figure out the linear speed for any location on a globe Earth.
Well, let's see. What has Jeran done so far? He's attempted to portray math as some sort of hoax that's been perpetrated on us by all those really smart kids. He's mangled the concepts of uniform circular motion, and now he's going to spend several minutes calculating the angular speed of a bunch of different points on the Earth. I think we'll just skip that part and move on to centripetal force. That's where it's going to get interesting.
We can simply look at centrifugal versus centripetal force to see another glaring example, and we can find more of the quote-unquote tricks of the trade. Centrifugal force is the moving or tending to move away from the center, versus centripetal force, which is the moving or tending to move towards a center. If you forget which is which, like I did for a while, an easy way to remember is to think of the F and the P. When I see the F, I think of flying off or flying away, and when I see the P, I think of pulling towards the center. So maybe that will help you a little as well. Now watch the trick here. The formula for centrifugal force is the centrifugal force equals the mass times the velocity squared over the radius, and the answer is in newtons. And the formula for the centripetal force is force equals mass times the velocity squared over the radius, and the answer is in newtons. Wait, aren't they the same? One for the force flying out and away, and then the other is the force pulling inward? Then you might see that in the general theory of relativity, that it just so happens that gravity and the centrifugal force are equivalent.
No, Jeran. Gravity and the centrifugal force are most definitely not equivalent. You're not weightless, are you?
In order for something to stay still while on a spinning platform like a merry-go-round, they say that all the forces need to add up to a zero vector. Well, to do that, you need the fly-away force to equal the pulling-in force. So when you include our weight, which they say is because of gravity, then you can start to see the mathematical tricks involved. Your senses go right out the window. Really, Jeran, doesn't science require our sense of observation and depend on our senses? Nope, not even close. Let's let Neil deGrasse Tyson tell us so we are all clear here about science and our senses.
Yeah, that's so what you learn when you study science in general, but astrophysics especially, that you no longer invoke your senses to judge what makes sense, or you no longer invoke your personal philosophies to judge what should be true. The universe is what it is, and it really doesn't care about your senses. Yeah.
Oh, okay, Neil. We are no longer to use our senses to judge what makes sense. The universe is what it is and doesn't care about your senses. And we can start to see why. Because they have built the universe mathematically, and only those skilled in those equations that have been made up are equipped to explain the world. How the universe they built using the math they constructed works. No deception can possibly work there. Because if you begin to invoke our own senses and to question what they have built, scary things begin to happen as the world they built begins to show signs of being a worldview, a religion masked by mathematical fact. We've all been had, ladies and gentlemen. So the site is called the Physics Classroom. This is, I guess, for children. It starts out talking about acceleration, then gives the geometric proof of inward acceleration. But we're going to go down a little bit further here so we can see an experiment or a test. So let me read you this from Direction of the Acceleration Vector. It says, objects moving in circles at constant speed accelerate towards the center of the circle. The acceleration of an object is often measured using a device known as an accelerometer. A simple accelerometer consists of an object immersed in a fluid such as water. Consider a sealed jar that is filled with water. A cork attached to the lid by a string can serve as an accelerometer. To test the direction of acceleration for an object moving in a circle, the jar can be inverted and attached to the end of a short section of a wooden 2x4. A second accelerometer constructed in the same manner can be attached to the opposite end of the 2x4. If the 2x4 and accelerometers are clamped to a rotating platform and spun in a circle, the direction of the acceleration can be clearly seen by the direction of the lean of the corks. As the cork-water combination spins in a circle, the cork leans towards the center of a circle. The least massive of the two objects always leans in the direction of the acceleration. In the case of the cork and the water, the cork is less massive on a per milliliter basis, and thus it experiences the greater acceleration. Having less inertia, owing to its smaller mass on a per milliliter basis, the cork resists the acceleration the least and thus leans to the inside of the jar towards the center of the circle. This is the observable evidence that an object moving in a circular motion at constant speed experiences an acceleration that is directed towards the center of the circle. This is complete nonsense. The water is being pushed to the outside, just like in the gravitron, just like in the merry-go-round of death, just like in any merry-go-round, just like in anything spinning. The water is flying towards the outside, which is pushing the lighter cork towards the middle. This here actually says, the cork of the water accelerometer points inward towards the center of the circle when placed upon this rotating platform, thus indicating an inward acceleration for circular motion. Wow.
So it can't work like that, huh? Hey, y'all watch this. Somebody hold my beer. Today we're going to look at the direction of acceleration in a rotating frame of reference. So what I've done is constructed a very crude little device here. Just a carriage bolt, a little carriage that I can sit on the bolt like so. So it'll spin, and it's made to hold my cell phone. My cell phone has got a linear accelerometer application on it. So what we have is green is the y-axis, acceleration that way would be toward the center, and red is the x-axis, so acceleration that way would be up or positive. And you'll see that when we rotate this thing. So what I'm going to do, let me unlock the screen. Let's see, we got to get the scale back. Let's get it back to, there we go. So now the scale vertically is from -2 to +2 meters per second squared. I'm going to turn the assembly around this way. Okay, and you see the accelerometer reacting to it maybe. I'll show it to you in a second. What I'm going to do is just spin this clockwise. So here we go. All right. Now let me pause that, because I gave it a pretty good spin. That's what we just did. The acceleration, as you see, that's the y-axis, the green. The acceleration was that way, in toward the center. Just like the book says. The red is the x-axis. It shows negative, but that's because we're spinning it this way. So it's actually accelerating not in the positive direction for the x-axis, in the negative direction. So there we have it. Want to do it again? Let me unlock the screen. This time, let me go back to better scale. Okay, there's -10 to +10. I'll move it around here. We'll do it one more time. Here we go. And hit the pause button. Nope, that was a mistake. That wasn't pause, that was reset. We'll try it one more time. Hey, I never said I was any good at this. Here we go. One more time. 3, 2, 1. Now the pause button. There we go. And again, there's the acceleration on the y-axis, that direction, in toward the center. There's the acceleration, that direction, the red line, that direction, and that's from me spinning it. So, see, science books are right. Well, now, don't we feel like the fool, huh? Let's talk about uniform circular motion. If you're on the circle there on the left at position A at about like where the 3 o'clock would be, your velocity vector would be vertical, straight up. As you rotate around to position B at the top of the circle, your velocity vector would be to the left, As you continue to rotate to position C, your velocity vector is straight down. That velocity vector is rotating in a circle. Something has to pull it around in the circle. That something is centripetal force. There is an apparent centrifugal force. It's the imaginary force that acts in the opposite direction. But it's not a real force. Centripetal force is real. Now, if you're spinning in a circle like that, and you reach position B where I've put the yellow dot, and you let go, you might think that you'll end up there where the yellow dot is. That may be what you're thinking. That is not what happens. You will continue along that vector, the velocity vector, from position B, and you'll end up over here. You can prove this to yourself just by taking any weight and putting it on a string, swinging it in a circle, and then letting go. And notice which direction it goes from the instant that you turn loose. It does exactly what this diagram is showing you. So let's talk about uniform circular motion, and we'll do it for the Earth. We have T is the period of rotation in seconds, R is the radius of the Earth in meters, omega is the angular velocity, which is 2 pi over t in radians per second. The velocity is omega times the radius, and that gives us a velocity, this is at the equator, of 463.82 meters per second. Centripetal acceleration is v squared divided by r. Work the numbers, and you find out that at the equator, the centripetal acceleration is 0.033 meters per second. Now you know the acceleration of gravity is 9.81 meters per second. Centripetal acceleration is only about 0.3% of g. That means if the acceleration at the North Pole is 9.81 meters per second squared, at the equator it would be 9.78 meters per second squared. That would make less than a pound difference in your body weight. That's the reason you don't notice it. That's why you can't feel it. That's why you don't fly off the ball. Some of this isn't obvious. This is a perfect example of why you can't trust your senses all the time. Sometimes you can, but not necessarily. Let's listen to Neil deGrasse Tyson one more time.
Yeah, that's so what you learn when you study science in general, but astrophysics especially, that you no longer invoke your senses to judge what makes sense, or you no longer invoke your personal philosophies to judge what should be true. The universe is what it is, and it really doesn't care about your senses. Yeah.
So, Jeran, let me leave you with a few thoughts. First of all, math isn't fiction. It perfectly describes the reality we experience every day. Science isn't a conspiracy that's out to trick you, and your senses aren't always right. You know, when you've been as demonstrably wrong about centripetal force as you've just shown you are, isn't it just possible that you're wrong about a lot of other things, including the shape of the Earth? So hey, thanks for watching. I hope you enjoyed it. If you did, don't forget to like and subscribe, and we'll see you on the next one.